Rio Hurtado Valley in the Andean foothills of north-central Chile. The night of July 1st, 2025, the clock on the Atlas Robotic Survey Telescope, designated by the Minor Planet Center as Observatory W68, reads just after local midnight. The half-meter right Schmidt is pointed at a dense patch of sky near the constellation Sagittarius, toward the galactic center, toward the largest population of stars the human eye can see. The telescope is unattended. It is a near-Earth object survey. It scans for things that move. Several thousand kilometers across the Pacific, in Honolulu, an astronomer named Larry Denyu of the University of Hawaii Institute for Astronomy is reviewing the night's detection chain. Most of what comes through is known asteroids. The software flags streaks. The software cross-checks them against catalogues. One streak does not match anything. The streak sits inside the galactic center starfield, where the stars are so densely packed that picking out a single moving object is the kind of work the human eye is not built for. The streak is faint, magnitude 18 or so. It is moving against the background. Deno pulls the orbit fit. The numbers come back wrong. The eccentricity is greater than 6. Not 9/10, not 1.1, 6.14. The hyperbolic excess velocity, the speed the object will retain once it has cleared the gravity well of our sun, is 58 kilometers per second. Nothing in the solar system moves like that. Deno has, at this moment, become the third human being in history to look at an object that did not form in our solar system. Tonight we are going to walk through what he found. You do not need to hold every number. Some you will. That is enough. The light from this small object had been on its way for longer than anything that ever crawled out of an ocean on Earth. We can take our time with it. Now, let us pull back. Let us look at where this streak sits in the order of things, and what kind of instrument was watching when it arrived. The Atlas survey was not built to find interstellar visitors. It was built to find things that might hit us. The acronym stands for Asteroid Terrestrial Impact Last Alert System, and it was designed at the University of Hawaii by John Tonry and Larry Deno and their colleagues to give the Earth a few weeks of warning before the impact of an asteroid large enough to flatten a city. The first Atlas unit came online in 2015 on the summit of Haleakala. A second followed at Mauna Loa. 2 more were added later, one in Sutherland, South Africa, and one at Rio Hurtado in Chile. The Chilean unit came online in 2022. 4 robotic telescopes on 3 continents scanning the entire visible sky every 24 hours. They were built for proximity, for things close to home. The system works by repetition. Each part of the sky is photographed 4 times a night, with about a 15-minute gap between exposures. The software compares the 4 frames and flags anything that has moved between them. Most of what it flags is satellite debris. Most of the rest is known asteroids. A small fraction is new. A smaller fraction is unusual. Tonry and Deno expected the system to find 1 Tunguska-sized impactor per decade. They did not expect it to find anything that came from outside the gravity of the sun at all. But the sky is not what we expect. The sky is what is there. The history of objects from outside our solar system, as a category we can name and write about and catalogue, is exactly 7.5 years old at the moment Deno opens this data file. Before October of 2017, every comet and every asteroid humanity had ever recorded belonged to our sun. They had been here since the formation of the disk. They were our own. Then a Pan-STARRS technician on Haleakala named Robert Werrick noticed a streak that refused to fit any solar orbit. The object was given a Hawaiian name, Oumuamua. It means a messenger from afar, arriving first. It was small, perhaps 200 meters long, oddly elongated, tumbling, behaving in ways that nobody quite understood. It passed through the inner solar system in 41 days and was gone before any larger telescope could photograph its shape. 2 years later, in August of 2019, a Crimean amateur astronomer named Gennady Borisov, working with a telescope he had built himself, found the second one. They named it 2I Borisov. It looked and behaved like a comet, only stranger in chemistry. It carried more carbon monoxide than any solar comet anyone had ever sampled. It came in, it lit up, it left. These 2 visits, in 2 years, after 2.5 centuries of careful sky surveys, finding nothing of the kind, suggested something quietly enormous. that the galaxy is full of objects like this, that stars routinely shed material into the dark between them, that what passes through our neighbourhood is not unusual at all. It is only that, until very recently, we did not have the eyes to see it. The numbers Deno is now looking at, in the early hours of July 2nd, 2025, are the third such record. The provisional designation that comes out of the Minor Planet Center automated pipeline that morning is A11PL3Z, a neutral string, a placeholder, the kind of name given to a thing the system does not yet know what to do with. Within hours, the discovery is reported. The astronomical community begins to look at it. The Deep Random Survey confirms the position. The Lowell Discovery Telescope in Happy Jack, Arizona, confirms it again. The Canada-France-Hawaii Telescope on Mauna Kea joins in. By the end of the 2nd of July, the Nordic Optical Telescope on La Palma has imaged the object, with one of those observations made by David Dewitt and Jane Liu, who together discovered the Kuiper Belt in the early 1990s. Marco Micheli of the European Space Agency's Near-Earth Object Coordination Centre at Frascati in Italy refines the orbit. Davide Farnocchia of the Centre for Near-Earth Object Studies at NASA's Jet Propulsion Laboratory in Pasadena runs his own orbit determination pipeline. The numbers agree. Eccentricity, 6.14135, the most hyperbolic orbit ever recorded. Inclination, 175.1 degrees, almost perfectly retrograde, moving against the direction of the planets. Perihelion, 1.356 astronomical units. The object will pass inside the orbit of Mars. It will not threaten Earth. The closest it will ever come to us is 1.8 astronomical units in December of 2025, roughly the distance from us to Mars on a bad day. None of these numbers, taken alone, would have caused anyone in the solar system to look twice. Many comets have high eccentricity. Many have steep inclination. Many cross the orbit of Mars. But the eccentricity is greater than 1. That single fact, that single line in the orbital solution, is the thing that changes the nature of what this object is. An eccentricity below 1 means a closed orbit. The object is bound to the Sun. It will return. An eccentricity above 1 means an open orbit. The object came from somewhere else, and it will go somewhere else. It is only passing through. An eccentricity of 6 is not a borderline case. It is unambiguous. This thing did not begin in our solar system. It will not end here either. On July 2nd, 2025, the International Astronomical Union issues a new designation. The provisional string AN11PL3Z is retired. The new name is 3E Atlas, catalogued in the cometry tradition, also as C2095N1. The numeral 3, the letter I for interstellar, and the survey that found it. Third interstellar, after Werek's Oumuamua, after Borisov's comet. The third confirmed body humanity has ever observed that did not form within the gravity of our own star. And here, before we go any further, is the first detail I want you to hold in your hand for a moment. The third interstellar object in history was not, in the strict sense, discovered on July 1st. It was only first noticed then. When astronomers went back through the archives after the announcement, they found the object in places nobody had thought to look. The Zwicky Transient Facility at Palomar Observatory in California had imaged that patch of sky throughout May and June. The object is there in the data, faint and unrecorded, moving on its hyperbolic line. NASA's TESS satellite, which is in Earth orbit and stares at the sky to find exoplanet transits, had it in survey frames from the 7th of May through the 3rd of June, almost 2 months before Deno's screen flagged it. There are hints in the TESS data that the object was already faintly active at 6.4 astronomical units from the Sun, already venting something, already alive. And there is one more, and this is the one that astronomers will remember. On June 21st, 2025, 10 days before the discovery, the Vera C. Rubin Observatory on Cerro Pachon in Chile was running commissioning tests on its enormous new survey camera, the LSST cam. The camera was being checked. Calibration data was being taken. The shutter opened. Light fell on the sensor. Among the things in those calibration frames, recorded but not yet noticed, was 3I Atlas. Rubin had photographed the third interstellar visitor before anyone on Earth knew there was a third interstellar visitor to find. Consider what that means. The instrument that is about to begin its full survey operations the instrument that is expected, over the course of its 10-year run, to find perhaps 100 new interstellar objects, had already found one before its eyes were officially open. It had simply not noticed. The streak was a few pixels in a frame. The frame was a calibration test. Nobody had been told to look for a thing that did not yet exist in any catalogue. The sky was already showing us what was there. We had not yet asked the question that would let us see it. This is the texture of the moment we are in. The objects from other stars are arriving. They have almost certainly been arriving for as long as our solar system has been here. We have simply, in the last decade, built the instruments that can pick out a faint streak against the galactic centre. The Atlas telescopes can see things 10,000 times fainter than the dimmest stars our eyes register. The Rubin Observatory, once it begins its full 10-year survey in earnest, will see things fainter still, and it will see them everywhere, every clear night. Karen Meech at the Institute for Astronomy in Hawaii, who has worked on interstellar objects since the original Oumuamua paper in Nature in 2017, has said publicly that we should expect within the decade to be tracking these visitors on a monthly cadence. The sky has not changed, our instruments have. And on the morning of July 2nd, 2025, and Noboroninaman and Katikam, Larry Deno is looking at the third one. He does not yet know what its chemistry will turn out to be. He does not yet know that, when the James Webb Space Telescope is pointed at it in August, the spectrum will come back dominated by carbon dioxide in a ratio higher than almost anything ever measured in any comet, anywhere. He does not yet know that, when astronomers run the kinematic clock backward on its trajectory, the answer will place its origin in the thick disk of the Milky Way, among the most ancient stars our galaxy contains. That a paper by Asta Taylor and Darrell Seligman in the astrophysical journal Letters will give its age as somewhere between 3 and 11 billion years. That a separate analysis by Matthew Hopkins at Oxford will push that age higher still, possibly older than the Sun itself. He does not yet know any of this. None of us do. On July 2nd, the only thing we know, looking at the orbital solution, is that something came in from outside and that we managed to catch it on its way through. The rest we are about to discover. Now let us pull back, fellow night watcher, and consider what kind of question Larry Deno has just opened on the dark side of the Pacific in the small hours of July 2nd. Because the strange thing about that orbital fit, eccentricity 6.14, is not that it is exotic. The strange thing is that the universe should be full of objects like it, and that for most of the time humans have been measuring the night sky, we managed to find none of them. Consider the simple physics. A star forms by gathering material from a cloud of gas and dust. Around it, a disk forms. Within that disk, smaller bodies grow. Planets, asteroids, comets, the leftover fragments of 1,000 collisions and accretions. Some of those bodies settle into stable orbits around their host star. Some, less lucky, are flung outward by close encounters with the larger planets, or by their own slow drift, until they reach a velocity that exceeds the escape velocity of the star they were born around. After that, they are no longer bound to anything, or they cross the dark between the stars alone for whatever time the galaxy gives them. There is a number in the orbital mechanics of every star that decides whether a body belongs to it or not. Astronomers call it the escape velocity. It is the speed required to climb out of the gravity well of the star at any given distance. Near the Sun, escape velocity is around 600 kilometers per second. Out at the edge of the heliosphere, where the solar wind gives way to the cold interstellar medium, it has fallen to less than a kilometer per second. The instant a body's velocity exceeds this threshold, at any point in its journey, it is no longer bound. The Sun's gravity will slow it. The Sun's gravity will never bring it back. This process, the ejection of icy planetesimals during planet formation, is now understood to be one of the largest sources of mass loss from any forming planetary system. Models of our own solar system suggest that, during the chaotic first few 100 million years, a substantial fraction of the bodies in the outer disk were thrown out into interstellar space by Jupiter, Saturn, Uranus, and Neptune. The same is almost certainly true around other stars. Multiply that by the hundreds of billions of stars in our galaxy. Multiply that by the 10 billion years they have had to do it. The result is a population that should be staggering. The local interstellar medium, in our neighbourhood, ought to be drifting with small bodies on every conceivable trajectory. And yet for 2.5 centuries of organised astronomy, since the cataloguing of comets in the 1700s, we had recorded none of them. Every comet that astronomers had measured belonged to our sun. This was not because the universe was empty. It was because we could not see what was there. Consider what it takes to find a single faint streak, perhaps 100 meters across, perhaps a kilometer across, moving against a background of stars at a distance of several 100 million kilometers, at the magnitude where it begins to look like nothing at all. The light reaching us from such an object is a few hundred photons per second per square meter of mirror. The streak on the sensor is a few pixels wide. To detect it, the telescope must scan the sky often enough to catch it before it has crossed the inner solar system. The wider the field of view, the better. The more sensitive the camera, the better. And the more carefully the software can compare last night's image to tonight's image, the better still. And consider for a moment what those photons have already been through to reach a single mirror on a mountain. Light reflecting off the dusty surface of a comet at 4 astronomical units travels back across the inner solar system at 300,000 kilometers per second. Half an hour, give or take, between the surface of the comet and the surface of the mirror. In that half hour, the light threads the gravitational web of Jupiter and Saturn and Mars without bending in any meaningful way. The streaks arrive, 4 pixels long, on a CCD chip in a robotic enclosure in Chile. The software flags them. A human, in another time zone, looks at the screen. For most of the history of telescopic astronomy, this kind of survey was impossible. The instruments were too narrow, the sensors too slow, the comparison too laborious. Comets and asteroids were found one at a time by patient observers with logbooks. When Edmund Halley worked out in 1705 that a comet seen in 1531, 1607, and 1682 was the same body returning every 76 years, the calculation took him years and changed astronomy forever. But it did not tell us anything about objects that came from outside. Halley's comet is ours. So are the comets of Caroline Herschel. So is every one of the several thousand named comets in the catalogues that astronomers built up across the next 2 centuries. The very idea of an interstellar object was, for most of that time, theoretical. It belonged to the same category as gravitational waves or black holes. Something we suspected must exist, somewhere, but had not yet been able to confirm. By the early 2000s, the ratio of theory to observation had begun to shift. The Sloan Digital Sky Survey was photographing large patches of sky every clear night. The Catalina Sky Survey, the Linear Project, the Spacewatch program, all began to catalogue near-Earth asteroids at rates that would have been impossible a generation earlier. Pan-STARRS atop Haleakala in Maui came online in 2010 with a wide-field camera that could photograph the entire visible northern sky every several days. Within a few years, the rate at which new asteroids and comets were being added to the Minor Planet Center catalogue had climbed into the hundreds of thousands per year. And still every single object that was found belonged to the Sun. Astronomers in those years were watching for the wrong thing without knowing it. Every survey, every catalogue, every new asteroid added to the rolls was, in a sense, also a measurement of an absence. The absence was important. The absence was the universe telling us gently that we had not yet built the eyes we needed. The first paper to formally bound this absence was published in early 2017 by Tony Engelhardt, Robert Yedeker, and their colleagues before Oumuamua had been found. They reviewed the surveys that had been operating and concluded that the density of interstellar objects in our neighbourhood must be less than a certain ceiling, because otherwise we would already have seen one. The paper was a careful piece of work. Its number was an upper limit. A few months later, on the 19th of October 2017, the streak that Robert Werrick had flagged from Pan-STARRS on Haleakala began to look, increasingly, like nothing anyone had catalogued. By the end of that week, the orbit had been refit. Karen Meach at the Institute for Astronomy in Honolulu was lead author on a paper that would appear in Nature the following month, titled A Brief Visit from a Red and Extremely Elongated Interstellar Asteroid. The object that Werrick had found was given the formal designation 1I 2017 U1. The popular name, as we have already said, was Oumuamua, the first. It was a strange object even by interstellar standards. It tumbled with a period of around 7 1/3 hours. in a way that suggested it was very long and very thin. Best estimates placed it somewhere between 100 and 400 meters in its longest dimension, and only 30 or 40 meters wide. The ratio was perhaps 5 to 1, perhaps 10 to 1. No comet anyone had ever measured looked like this. No asteroid did either. The object was red, but not in the way a typical asteroid is red. It was reflective, but not as reflective as ice. It showed no coma, no tail, none of the venting one would expect from a body warming for the first time near a star. And yet it appeared to accelerate, slightly after perihelion, in a way that gravity alone could not explain. Meech and her colleagues had 41 days. 41 days between the time the object was found and the time it became too faint to follow. In those 6 weeks, hundreds of papers would eventually be written about it. Avi Loeb at Harvard would propose that it might be a light sail, an artifact of intelligence. Most astronomers disagreed, and continue to disagree. The mainstream explanation, refined over years, is that Oumuamua was probably a fragment of a much larger icy body, ejected from its home system long ago, depleted of most of its volatiles, with a residual coating of frozen hydrogen or nitrogen that quietly sublimated as it warmed near the sun, producing the small non-gravitational push that confused us. Whatever it was, it left. We never photographed its surface. We never resolved its shape. The Hubble Space Telescope got a single point of light. The best evidence we have for what Oumuamua looked like comes from variations in that point of light over a few hours of tumbling. The rest is inference. We extrapolated from a moving dot. 2 years later, almost to the month, the second one arrived. Gennady Borisov was an optical engineer at the Crimean Astrophysical Observatory in the village of Nauchnij on the southern coast of the peninsula. He had a small private observatory of his own on the grounds behind his home. He called it Margot. The telescope at Margot was a 65-centimetre reflector with optics that he had ground and assembled himself. He had built it. He had not bought it. On the night of August 30th, 2019, working with that telescope, Borisov found a faint smudge of light moving across the sky in a way that looked, at first, like a normal long-period comet. The orbit fit said otherwise. By mid-September, the eccentricity had been refined past 3. By the end of the month, no other interpretation was possible. The object that the world would come to call 2I Borisov, the second interstellar, was the first known interstellar visitor that looked, behaved, and chemically resembled a comet. It had a coma. It had a tail. As it neared the sun, it began to vent. Astronomers had time this time. Borisov had been spotted on its way in, not on its way out. There were months to study it. The Hubble Space Telescope photographed it. The Atacama Large Millimeter Array in northern Chile measured the gas in its coma. Dennis Bodowitz at Auburn University and Martin Cordner at NASA Goddard reported that the comet carried an extraordinary amount of carbon monoxide. The CO to water ratio was nearly 10 times higher than in any solar system comet ever measured. Borisov had formed somewhere very cold, somewhere where carbon monoxide ice persisted in the bulk material of the body for the entire history of its home star. Then it broke apart. In late 2019 and early 2020, as Borisov rounded the sun, its nucleus fragmented. Pieces drifted away. The comet, what was left of it, continued on its hyperbolic path back into the dark. We watched it for as long as we could, and then it was gone. That was December of 2019. Almost 6 years would pass before the third one arrived. In those 6 years, the cadence of expectation shifted. Karen Meech in Hawaii had been among the first to argue, in print, that the discovery of 2 interstellar objects in 2 years was not a coincidence. It was a baseline. The Pan-STARRS surveys, the Atlas surveys, the Catalina Sky survey were now sensitive enough to find such things, and the Vera C. Rubin Observatory, when it began full operations, would be sensitive enough to find them in numbers. The Rubin Observatory is a single instrument that should change the cadence of this entire discussion. It sits on Cerro Pachon in the Andean foothills of Chile, not far from the Atlas Chile unit at Rio Hurtado. Its primary mirror is 8.4 meters across. Its camera, the LSST cam, holds 3,200 megapixels of sensor. It is the largest digital camera ever built. Over the next 10 years, it will photograph the entire visible southern sky every 3 to 4 nights, producing a project called the Legacy Survey of Space and Time. When complete, that project is expected to record around 20 billion individual astronomical objects. The instrument's first official survey observations were scheduled for late 2025. The mirror had been cast, the camera installed, the software calibrated. Commissioning images had been taken throughout the spring and early summer, and it is in those commissioning images, on the 21st of June, 2025, 10 days before the Chilean Atlas unit caught a streak in the dense fields of Sagittarius, that the third interstellar visitor first appears in the data of human civilization. Caught by chance, before anyone knew to look for it. Hold the symmetry of that moment in your mind, fellow wanderer. The first interstellar object, Oumuamua, was found in 2017 by a man named Werik on a mountain in Maui. The second, Borisov, in 2019, by an amateur on the southern coast of Crimea with a telescope he had built himself. And the third was first noticed in 2025 by a robot in Chile, while a much larger robot, less than 200 kilometers to the south, had quietly photographed it in calibration tests 10 days before. We did not learn this from a press conference. We learned it from looking back, weeks later, through stored data at a streak that nobody had been told to find. The instruments have started to outpace us. The sky is no longer waiting for our attention. It is instead beginning to find us back. Now let us return to the man at the screen in Honolulu, fellow night watcher, and look more closely at what he was looking at. The system that flagged the streak on the morning of July 2nd, 2025, has a name that says exactly what it was built for: the Asteroid Terrestrial Impact Last Alert System. Atlas. The name is not modest. It promises that if a city-killing rock is on its way toward the Earth, this network will catch it with enough days of warning that something can be done. Not years, days. A last alert. The acronym is a kind of confession about how much our forecasting still depends on luck. Atlas was conceived around 2013 by John Tonry, an astrophysicist at the University of Hawaii Institute for Astronomy, who had spent decades working on instrumentation, including some of the foundational work on the camera that would become pan-stars. Tonry's pitch to NASA was deceptively simple. Build a small network of robotic telescopes with very wide fields of view and very fast cadence. Do not chase faint things. Chase moving things. Photograph the entire visible sky every 24 hours, twice. Find anything that has shifted between exposures. Cross-check that shift against the catalogue of known objects. If it does not match anything known, flag it for a human. The first unit was built on Haleakala, the same mountain that had been hosting pan-stars for years. The second went up at the Mauna Loa Observatory on the Big Island, at the high northern slope of an active volcano. By 2020, 2 additional units had been added in the southern hemisphere, where the sky offered different coverage. One at the Sutherland Observatory in the High Karoo of South Africa. One in Chile at the El Source site in Rio Hurtado, a small dark sky valley in the Coquimbo region, several hundred kilometers north of Santiago. Each unit is, by the standards of modern professional astronomy, a small instrument. Its primary mirror is 50 centimeters across. Its design is a Wright-Schmidt configuration with a wide field, about 30 square degrees per exposure. By comparison, the full moon is about half a square degree. Atlas can photograph the equivalent of 60 moons at once. Its cameras are CCDs of more than 100 megapixels. Its limiting magnitude is around 19.5, depending on conditions. There are larger telescopes by every measure, but for the job of finding things that move, on time every night, this network was built to be enough. The Chilean unit, with the Minor Planet Center designation W68, came online in 2022. It was, on the night that mattered, less than 3 years old. Its mirror had been polished in Maui. Its enclosure had been assembled in the Coquimbo region. Its software was the same software that ran on Haleakala and Sutherland and Mauna Loa, written and maintained by a small team in Honolulu. Larry Deno is one of the people who maintains it. He is not the kind of astronomer who looks through an eyepiece. By his own description, he is a software engineer who happened to fall into astronomy. He had worked on the pan-stars pipeline before joining Atlas. His job, since the network began, has been to keep the data flow alive. The telescopes take exposures. The exposures are reduced. The reduced images are compared against templates. Moving sources are flagged. The flags are sorted by confidence. And every morning, in Honolulu time, someone like Larry Deno opens the queue. On the morning of July 2nd, 2025, the cue from Chile included a streak in the dense fields near the galactic center, in the constellation Sagittarius. This was an unusual region for an interesting detection. The galactic center is a forest of stars. Even good algorithms struggle to extract a faint moving source from a background that thick. Most of what came out of those fields was rejected by the pipeline before a human ever saw it. This one survived. The orbit fit. When Deno ran it, came back with an eccentricity of around 6.14. The first few times he saw a fit like this, he probably looked again. It is the kind of number that, by the standards of normal solar system mechanics, suggests an error somewhere upstream. A typo in coordinates, a misidentified field star, a flaw in the catalogue used for astrometry. The default assumption, when a number this strange comes out of a pipeline, is that the pipeline has lied. But the streak had multiple detections, spread across the exposures from that Chilean night. The astrometry was consistent. The fit was real. Deno forwarded the detection to Marco Micheli at the European Space Agency's Near-Earth Object Coordination Centre in Frascati, Italy. Micheli ran his own confirmation pass. Within hours, additional images were being requested from other telescopes. The Deep Random Survey, a project that watches for transient sources from a series of small instruments scattered across the globe, found the streak in its own archive. The Lowell Discovery Telescope in northern Arizona slewed to the coordinates and confirmed motion. The Canada-France-Hawaii Telescope on Mauna Kea did the same. A11PL3Z, that was the provisional designation. 5 characters strung together, the way the Minor Planet Center tags any new candidate before its nature is settled. The world's astronomical infrastructure does not announce discoveries. It catalogues them quietly in a system that has been doing this kind of work since the 1800s. Within a day, Davide Farnocchia at NASA's Jet Propulsion Laboratory in Pasadena had begun refining the orbit. Farnocchia leads orbit determination for the Center for Near-Earth Object Studies, the part of JPL whose job is to figure out where things are going and how confident we are about the answer. His fits, drawing on the additional observations from Lowell and CFHT, tightened the eccentricity. 6.14, the number held. On the 2nd of July, the IAU issued the formal designation, 3I Atlas, the third interstellar. The catalogue alias in cometary nomenclature was C1T25N1, indicating a comet discovered in the first half-month of July 2025 by the Atlas network. The third eye in human history, the first one found in a southern hemisphere survey, the first one found in a region of sky so crowded that statistically it should have been hidden. And then the pre-covery work began. This is one of the quiet pleasures of modern surveys. Once an object has been identified and its orbit has been calculated, astronomers can look backward through their archives to see whether the same object was sitting, undetected, in earlier images. The mathematics is just a matter of running the orbit in reverse and checking whether any survey had a pixel pointed at the right coordinate at the right time. Modern surveys photograph so much sky so often that the answer is usually yes. In the case of 3I Atlas, the answer was unusually rich. The Zwicky Transient Facility, a survey based at Palomar Observatory in Southern California, found the object in frames going back to the 22nd of May. The Weizmann Astrophysical Observatory in Israel had a detection from earlier still, on the 21st. Most striking, the Transiting Exoplanet Survey satellite, the NASA mission, designed to find planets orbiting nearby stars, had quietly recorded the object in its wide-field data between the 7th of May and the 3rd of June. A paper by Adina Feinstein and her colleagues, which would appear in the Astrophysical Journal Letters later that summer, established that TESS had seen 3I Atlas when it was still 6.5 astronomical units from the Sun, almost 2 full months before any human astronomer flagged it. But the most poetic of the pre-covery detections came from a different mountain in Chile. The Vera C. Rubin Observatory on Cerro Pachon, only some 150 kilometers from the Atlas Chile unit at Rio Hurtado, had been running commissioning exposures throughout the spring and early summer of 2025. Its formal scientific operations had not yet begun. The first images from the LSS TCAM were being analysed largely as calibration tests. On the 21st of June, 10 days before Atlas Chile caught its streak, Rubin's primary mirror had photographed a region of sky that included the slow-moving comet from interstellar space. The exposures were not flagged at the time. The object was a few faint pixels in a frame full of other faint pixels. The pipeline had not been tuned yet to look for things like this. It took another month after the IAU designation for someone to look back through the Rubin commissioning data and find it. This is worth sitting with, fellow night watcher. The largest digital camera ever built had a perfect record of 3i Atlas before anyone knew to ask. It was sitting on the disk in the southern hemisphere, in a building near the same valley where the Discovery telescope would, 10 days later, take the image that caught a human's attention. We have been outpaced by our own instruments. The eyes we have built are now seeing things faster than the brains behind them can recognize. There is something about that fact that, when you really hold it, changes the texture of what astronomy is becoming. For most of human history, the limitation was the eye. We could not see far enough, or sensitively enough, or often enough. Now, increasingly, the limitation is attention. The data flows, the instruments record, the streaks appear in the archive, and somewhere a person has to know to look. Now let us turn to what we found once we knew to look. The first follow-up observations of 3i Atlas, in the days after the 2nd of July, began with the simple goal of confirming what kind of body it was. An asteroid, a comet, something else. At a heliocentric distance of around 4.5 astronomical units between the orbits of Jupiter and Mars, an icy body would already be warm enough to begin venting volatiles. An inert rocky body would not. The presence or absence of a coma in those first images would decide between the two. The first deep images came from the Nordic Optical Telescope on the island of La Palma in the Canary Islands. David Jewett of the University of California, Los Angeles, and Jane Liu, a longtime collaborator who had spent much of her career in Norway and at MIT Lincoln Laboratory, requested time on the morning of the 2nd. The two of them had been doing this kind of work together since the late 1980s. In 1992, they had jointly discovered the first object in what would become known as the Kuiper Belt, the disk of icy bodies beyond Neptune. 3 decades later, they were among the first to point a telescope at the third interstellar visitor. Their Nordic Optical Telescope images showed what they had hoped to see: a small, faintly diffuse glow around a point source, a coma. 3i Atlas was a comet. Within 48 hours, the European Southern Observatory's very large telescope at Cerro Paranal in northern Chile had also begun its observation campaign. The Teide Observatory of the Instituto de Astrofísica de Canarias on Tenerife had photographed the object. The Gemini South Telescope, on the same mountain as the Rubin Observatory, had imaged it through its GMOS spectrograph. By the end of the first week, more than a dozen of the largest telescopes on the planet had pointed at a single faint smudge of light moving through Sagittarius. Karen Meach entered the story then. Meach, at the Institute for Astronomy in Honolulu, is the same astronomer who, in 2017, had been lead author on the first paper describing Oumuamua. She had spent the years between then and now working on a long list of projects on the chemistry of cometary bodies and the boundaries of the solar system. When the IAU designation came through for 3i Atlas, she was, by every measure, the most experienced living scientist on the subject of interstellar visitors. The third one had been waiting, in some sense, for her. On the 5th and the 14th of July, Meek led spectroscopic observations using 2 instruments. The first was the Gemini Multi-Object Spectrograph on Gemini South in Chile. The second was the SPECS Near-Infrared Spectrograph on the NASA Infrared Telescope Facility on Mauna Kea. The spectra, taken across visible and near-infrared wavelengths, would eventually become part of a much larger composite picture of the comet's chemistry. But on those 2 summer nights, the work was simpler. Confirm the comet's composition. Get the first hint of what it carried with it from wherever it had come. The early spectra showed nothing unusual at first glance. The colours were red, like many comets at large heliocentric distances. There was no obvious emission from the typical molecular species. The object was, at 4 astronomical units, still cold enough that most of its volatiles were locked inside the body, and the coma was dominated by dust rather than gas. That would change. The temperature was rising, the comet was inbound, and somewhere in the spectral structure of those first images, hidden in the way light bounced off particles too small to resolve, was the beginning of a story that would only fully reveal itself a month later, when the James Webb Space Telescope joined the campaign. The James Webb Space Telescope had been operating from its position at the Sun-Earth L2 Lagrange point for just over 3 years on the morning that it pointed itself at the third interstellar visitor. It had been launched on Christmas Day, 2021, from the European Space Agency's spaceport at Kourou in French Guiana, on top of an Ariane 5 rocket. The journey to L2 took 30 days. The unfolding of the sunshield and the deployment of the segmented gold-coated mirror, in a sequence of more than 300 separate mechanical actions, took several weeks more. First science observations had been released in July 2022. Since then, the instrument had been the most powerful astronomical observatory ever built. On the 6th of August 2025, Webb pointed at a faint-moving comet inside our own solar system at a heliocentric distance of 3.32 astronomical units. The observation used the near-infrared spectrograph, an instrument called NIR-SPEC, which disperses light from very faint sources into its constituent wavelengths between 0.6 and 5.3 microns. The team that had requested the time was led by Martin Cordner, an astrophysicist with a joint appointment at NASA's Goddard Space Flight Center in Maryland and the Catholic University of America in Washington. Nathan Roth of American University and Goddard was the co-lead. Their proposal had been one of the rapid response observations the Institute reserves for transient phenomena, the kind that cannot wait for the next regular allocation cycle. The exposure was short by JWST standards. Less than an hour of integration, the resulting spectrum, when it came down through the Deep Space Network and was reduced at the Space Telescope Science Institute in Baltimore, contained more information than every previous spectrum of any interstellar object combined. The dominant emission feature, by a wide margin, was carbon dioxide. Now let us hold what this means for a moment, fellow night watcher. In the comets of our own solar system, the gas that drives a coma is overwhelmingly water vapor. Frozen water makes up most of the volatile inventory in a typical cometary nucleus. At distances inside about 3 astronomical units from the Sun, sunlight is warm enough to sublimate water ice directly from solid to vapor, and that water carries everything else with it. Other species, including carbon monoxide, methane, ammonia, methanol, hydrogen cyanide, and carbon dioxide, are usually present in trace ratios relative to water. In a typical short-period comet, the carbon dioxide to water ratio sits somewhere between 1 and 10%. In the extreme outliers of the long-period comet population, it can climb to 30%. In 1 or 2 unusual cases, it has approached 50%. The ratio in 3I Atlas, when Cordner and Roth finished their reduction, was 7.6. Not 7.6%, 7.6. Carbon dioxide outnumbered water in the coma of this interstellar visitor by a factor of 7. The production rate of carbon dioxide at 3.32 astronomical units was 129 kilograms per second. The production rate of water in the same observation was 6.6 kilograms per second. The paper that Cordner, Roth, and their collaborators wrote on the basis of this single spectrum, published in the Astrophysical Journal Letters on the 25th of August, 2025, would become one of the most cited works on any interstellar object yet written. That paper, in its conclusion, said something quietly remarkable. It noted that 3I Atlas may preserve a record of the chemistry of the protoplanetary disk in which it had formed, and that the carbon dioxide-dominated composition was unlike anything yet observed in any comet of our own solar system, and pointed toward conditions in which water ice was rare, and carbon-bearing volatiles were abundant. 2 weeks after the JWST observation, the NASA SPHEREx mission, an Earth-orbiting infrared all-sky survey that had only begun science operations earlier in 2025, observed 3I Atlas directly. SPHEREx is much smaller than Webb. Its mirror is 20 centimeters across. But its design is unusual. It takes a low-resolution spectrum of every point of the sky, simultaneously, in 96 different wavelength bands. On the 21st of August, 2025, SPHEREx confirmed the presence of solid carbon dioxide ice and water ice on or near the cometary nucleus itself. The spectral fingerprints in the infrared are unambiguous. Now let us look back at what had already been measured and what was still to come in the weeks between these observations. On the 21st of July, 2 weeks before Webb's spectrum, The Hubble Space Telescope had taken its own images of 3I Atlas. Hubble by then had been operating in low Earth orbit for 35 years. Its primary mirror, 2.4 meters across, had been launched in 1990 on a space shuttle, repaired in 1993 after the discovery that its surface had been polished to the wrong shape, and upgraded multiple times by astronauts in the years since. By 2025, its instruments were almost entirely beyond their original design lifetimes. They were also still some of the sharpest eyes in orbit. The images were taken through the Wide Field Camera 3. The lead author on the resulting paper was David Jewett of the University of California, Los Angeles. Jewett, with Jane Liu, had jointly discovered the first object beyond Neptune in the Kuiper Belt in 1992. 3 decades later, his Hubble images of 3I Atlas resolved the nucleus and the inner coma at a resolution that no other telescope on the ground or in space could match. The nucleus in those images was a single unresolved point. Jewett's team could not measure its diameter directly. What they could do was bracket it. The faintness of the central source, after careful subtraction of the surrounding dust coma, set a strict upper limit on how large the body could be, assuming a typical dark cometary surface. The lower limit came from the dust production rate, which required some minimum amount of mass to be venting volatiles. The two numbers met somewhere between roughly 600 meters and 5.5 kilometers across. Jewett's preferred value in the paper that appeared in the Astrophysical Journal Letters in August was a nucleus radius of 1.3 kilometers, plus or minus 200 meters. The total mass of the body, on that estimate, was about 44 billion kilograms. A small object by every measure, a pebble against the scale of a planet, a pebble that had been falling toward the sun for longer than the sun had existed. Now let us hold that for a moment. The next round of measurements came from the Very Large Telescope at Cerro Paranal in Chile. The VLT is 4 separate 8.2-meter telescopes, mounted in a row on a mountain in the Atacama Desert at an altitude of 2,600 meters. The European Southern Observatory runs them. Among their many instruments is a polarimeter called FORS2, which measures not only how much light arrives from a target, but also the direction in which that light is polarized. Polarization, in this context, encodes information about the dust grains that scatter sunlight in a coma. Different grain sizes, different compositions, and different shapes leave different polarimetric fingerprints. The team that observed 3I Atlas with FORS2 was led by Stefano Bagnulo at the Armagh Observatory and Planetarium in Northern Ireland, The observations, taken in late summer 2025, produced what Bagnulo and his colleagues called an extreme result. The negative linear polarization in the anti-solar direction of the coma reached 38%. To put that number in context, the negative polarization of dust in normal solar system comets at similar phase angles sits between 1 and 5%. Even the most polarimetrically extreme comets, like Hale-Bopp, at its brightest in 1997, did not exceed about 8%. The dust around 3I Atlas, in other words, was scattering sunlight in a way that no dust in our own neighbourhood had ever been observed to scatter it. Bagnulo's interpretation, in the paper posted to the Arxiv preprint server in September, was that the coma was rich in sub-micron silicate particles, smaller and more uniform in size than the dust in any solar system comet ever measured. Sub-micron, smaller than a wavelength of visible light. The particles were on the order of 1/10,000th of a millimetre across. Trillions of them, drifting in the slow wind of an outgassing nucleus, scattering sunlight at angles that physics could explain only if they were impossibly small and impossibly clean. Whatever process had cooked these grains, in whatever ancient stellar nursery they had been forged, had left them more pristine than any cometary dust we knew. By the middle of August, a third measurement had come in. Tony Santana Ros, an astronomer at the University of Alicante and the Institute for Space Sciences in Barcelona, had been monitoring 3I Atlas night after night with a small network of telescopes to construct a light curve, a record of how the brightness of the object varied as it rotated. Comets are rarely spherical. As they spin, the cross-section presented to the observer changes and the integrated brightness rises and falls in a periodic pattern. From the period of that pattern, you can derive the rotation period of the nucleus. The pattern, for 3I Atlas, repeated every 16.16 hours, give or take 100th of an hour. The object was tumbling slowly, not the chaotic multi-axis tumble that had made Oumuamua so strange in 2017, but a clean single-axis rotation, just over half an Earth day, long enough that, if you could stand on its surface, you would see the sun rise and set roughly once every 8 hours. It is worth, fellow wanderer, holding these three numbers together: 7.6, 1.3, 16.16. The first is the ratio of carbon dioxide to water in the coma. The second is the radius of the body in kilometers. The third is its rotation period in hours. None of them, in isolation, is the most extraordinary thing about 3i Atlas. The most extraordinary thing about it was something nobody yet had measured at all. The most extraordinary thing was its age. That measurement would arrive in the second week of July 2025 through a different kind of analysis. Not photons, not chemistry, not light curves. A velocity vector. Now let us look at how that vector was unwound. When 3i Atlas was first announced, the JPL orbit determination team, led by Davide Farnocchia, had measured not only its perihelion distance and its eccentricity, but also the direction it had been coming from. The hyperbolic excess velocity, the speed the object would have had at infinity before the sun's gravity began to bend its path, was 58 kilometers per second. The vector pointed back along a trajectory that traced through the inner solar system, out past the orbit of Jupiter, out past the heliopause, and into the wider galaxy. Tracing it further still, under the assumption that the object had been moving inertially for tens or hundreds of millions of years, allowed the calculation of which population of stars in our galaxy was, on average, moving at the same velocity as 3i Atlas. This is a piece of analysis called galactic kinematics. The Milky Way is not a uniform population of stars. Older stars have higher velocities relative to the local standard of rest, because they have been gravitationally perturbed by a longer history of close encounters with other stars and giant molecular clouds. Younger stars, born in the thin disk near the galactic plane, have low relative velocities. Older stars in the thick disk have higher ones. The very oldest population, the halo, has the highest velocities of all. The teams that did this calculation for 3i Atlas were astronomers at the University of Michigan and the University of Oxford. Asta Taylor, at Michigan, was the first author of the paper that appeared in the astrophysical journal Letters in late July. Matthew Hopkins, at Oxford, published a parallel analysis through the Royal Astronomical Society in the same month. Both teams used the same data, the same kinematic models, the same orbit, and the same star catalogues. Both reached compatible conclusions, with overlapping error bars but slightly different point estimates. The number that Taylor's team reported was a kinematic age between 3 and 11 billion years. The number that Hopkins reported was a 68% confidence range between 7.6 and 14 billion years. The universe is 14 billion years old. There is something about this number that, the first time you really hold it, changes how you stand on the ground. The Sun, our star, formed about 4.5 billion years ago. The Earth congealed shortly after. Life on this planet appeared something like 3.8 billion years ago. The oldest individual organism currently alive on Earth, a bristlecone pine in the White Mountains of California, is just under 5,000 years old. Civilization, as a thing humans do, is 12,000 years old. And the comet that crossed the orbit of the asteroid belt in the summer of 2025 had been moving through the spaces between stars for, by the most careful measurement available, somewhere between 7 and 14 billion years. It was older than our Sun. Probably. If the Hopkins estimate held, it was older than our Sun by something on the order of 3 billion years. It was older than the elements that make up the rocks under your feet. The atoms in its body, except for hydrogen and a small amount of primordial helium, had been forged inside stars that had lived and died and seeded a younger generation of stars before our own had ignited. It had been a frozen wanderer when the cloud that would become the solar system had not yet collapsed. It had been a frozen wanderer when the cloud that would become the Sun's parent cloud had not yet collapsed. It had been falling slowly through the long currents of the thick disk of the Milky Way for a stretch of time longer than the entire history of every rocky planet in our system. And in the summer of 2025, it crossed our orbit and we measured it. Now let us look at what people did with that realization. In the weeks following the publication of Taylor and Hopkins's kinematic age papers, 3I Atlas, became the most discussed astronomical object in the world. The age was the headline, but it was not the only consequence. The age, in fact, deepened the rest of the story. Because if the comet was older than the Sun, then every measurement so far made of it was a sample of conditions in a part of the galaxy and a part of cosmic history that no other instrument had ever directly observed. The composition, the dust, the polarization, the rotation, the colour. All of it was a photograph of matter that had condensed before the Sun ignited. There were two responses to this realization. One was scientific, the other was something else. On the 16th of July 2025, a paper appeared on the Archive preprint server. The paper was titled simply, "Is the Interstellar Object 3 Atlas Alien Technology?" Its lead author was Avi Loeb, professor of astronomy at Harvard University, former chair of Harvard's astronomy department, and author of the 2021 book in which a similar question had been posed about the first interstellar object, Oumuamua. The paper had two co-authors, both former students of Loeb's. It was uploaded to Archive as a preprint, meaning it had not yet been through formal peer review. Loeb's argument condensed was that the orbital geometry of 3I Atlas was anomalous in a way that Oumuamua had not been. The inclination, near retrograde at 175.1 degrees, placed the object close to the ecliptic plane in a way that maximised the chance of inner-planet encounters. The trajectory passed within 0.194 astronomical units of Mars in early October. It would also approach Venus, Mercury and the Sun at closer distances than would be expected from a randomly oriented hyperbolic visitor. Loeb argued that the joint probability of all these geometric coincidences was small. Combined with the high entry velocity, the unusual non-gravitational acceleration components that some teams had reported, and the possibility that the carbon dioxide-rich coma might be reinterpreted as something other than natural sublimation, he argued that the alien technology hypothesis deserved serious consideration. Now let us follow the response. The response by the third week of July was firm. Christopher Lintott, professor of astrophysics at the University of Oxford, said in a public statement that the paper was poor work which did not reflect the evidence of an ancient comet. Steve Croft, an astronomer at the SETI Research Center at the University of California, Berkeley, said the level of evidence required to claim alien technology was much higher than what the paper had presented. David Kipping, an astronomer at Columbia University, who runs the Cool Worlds Research Group, posted a detailed statistical analysis showing that the geometric anomalies cited by Loeb were within the expected variance for a sample of 1. Jason Wright, an astronomer at Penn State University who has run a long-standing blog on technosignature science, wrote a point-by-point response in which he argued that the velocity, trajectory, and composition of 3I Atlas were all consistent with a natural body. By November, Wright had published a list addressing each of the 15 anomalies Loeb had progressively claimed, finding none of them sufficient to merit a technological hypothesis. The Loeb framing did not disappear from public attention. It continued to circulate in popular media throughout the autumn. The peer-reviewed astronomy community, however, treated 3I Atlas as exactly what every careful measurement said it was: a small, ancient, water-poor, carbon dioxide-rich comet from another stellar system, observed at the closest point of a one-time passage, behaving in ways that were unusual but compatible with the broader range of possibilities for material formed under different conditions. There was, however, one observation that the community ran anyway, the kind of observation that, if a positive result were obtained, would settle the question instantly. On the 18th of December, 2025, the Green Bank Telescope in West Virginia pointed itself at 3I Atlas. The Green Bank Telescope is a 100-meter dish operated by the Green Bank Observatory in the National Radio Quiet Zone of the Central Appalachians. It is the largest fully steerable single-dish radio telescope in the world. It is one of the instruments used by the Breakthrough Listen initiative, a privately funded 10-year program to search for technosignatures from astronomical targets. The observation was led by Sophia Sheik, a researcher at the SETI Research Center at UC Berkeley, with Steve Croft as co-lead. The frequency coverage spanned 1 to 12 gigahertz, the band in which an artificial transmitter operating at the power level of a household microwave would be detectable across the comet's distance. The observation listened for 6 hours. The result, posted to Archive at the end of December 2025, was a null detection. No artificial radio signal above 100 milliwatts of transmitter power was found. The interstellar visitor was, as far as the most sensitive radio search ever conducted on a solar system body could determine, radio silent. Let us return now to the comet itself, and to what it had been doing while these arguments unfolded. On the 3rd of October, 2025, 3I Atlas passed within 0.194 astronomical units of Mars, 29 million kilometers. By the standards of interstellar visitors, an extraordinarily close pass. By the standards of human assets in space, a close enough approach to be observed by multiple Mars-orbiting spacecraft. The European Space Agency's ExoMars Trace gas orbiter, which had been in Mars orbit since 2016, used its high-resolution CASIS imager to photograph the comet. Mars Express, the ESA orbiter that had been operating since 2003, did the same. NASA's Mars Reconnaissance Orbiter, the observation platform in Martian orbit since 2006, joined them. Even the Perseverance rover, on the Martian surface, was tasked to look up. It was the first time in the history of human spaceflight that a body from another star had been imaged from another planet. 2 weeks later, NASA's Parker Solar Probe began its own observation campaign. Parker Solar Probe is the closest spacecraft humanity has ever sent to the Sun. Its trajectory takes it through the solar corona on increasingly close approaches. From its position inside the inner heliosphere, between 172 and 195 million miles from 3I Atlas, it operated its wide-field imager for Solar Probe, an instrument called WISPR. WISPR captured roughly 10 images of the comet per day across an 18-day window. The images, processed by the United States Naval Research Laboratory team that operates the instrument, revealed the long, structured dust tail of the comet during the period when it was lost to Earth-based telescopes behind the glare of the Sun. On the 21st of October, 2025, 3I Atlas reached solar conjunction. From Earth's vantage, the comet passed almost directly behind the Sun. No optical telescope on Earth or in low Earth orbit could see it. For nearly 2 weeks, the only humans observing 3I Atlas were doing so from spacecraft in the inner solar system, looking sideways across the orbital plane at a faint object falling toward its closest passage, to a star whose light would never warm any planet it had ever known. On the 29th of October, 2025, at approximately 11:45 Universal Time, 3I Atlas reached perihelion, 1.356 astronomical units from the Sun, 203 million kilometers. The maximum heliocentric speed at that moment was 68.3 kilometers per second. The comet, in that instant, was moving faster than nearly any solar system body had ever been observed to move under the Sun's gravity at that distance. It would slow gradually from that point onward as the Sun's pull diminished behind it, but it would never stop. The trajectory was unbound. It would leave. In the days immediately surrounding perihelion, a team at the IRAM 30-meter telescope, on the Pico Veleta peak in Spain's Sierra Nevada, at an altitude of just under 3,000 meters, observed the comet in millimeter wave radio frequencies. The IRAM 30-meter is one of the largest millimeter telescopes in the world. The team was led by Nicolas Biver, an astronomer at the Paris Observatory, who has spent his career studying the molecular composition of comets. Between the 1st and the 3rd of November 2025, while the comet was at its closest and warmest, Biver and his collaborators detected hydrogen cyanide, methanol, carbon monoxide, formaldehyde, methyl cyanide, and carbon monosulfide in the coma. The paper would appear in Astronomy and Astrophysics in 2026. The detection of methanol and the cyanides confirmed that 3I Atlas contained the organic precursor molecules common to comets in our own system. The relative ratios of these species, however, were different. Carbon monoxide, in particular, was unusually abundant. Methanol was depleted relative to hydrogen cyanide in a way that hinted at chemistry under conditions different from the protoplanetary disk that birthed our own solar system. A second realization arrived in early 2026. On the 7th of January, the Subaru telescope on Mauna Kea observed 3I Atlas as it receded outbound past the orbit of Mars. By then, the comet had passed perihelion. It had warmed in sunlight and was now slowly cooling again. The Subaru measurement, surprisingly, found that the carbon dioxide to water ratio in the coma had dropped substantially from its August value. The water rate was now closer to parity with the carbon dioxide rate. The composition of the coma had not been fixed. It had evolved as the comet heated, and then again as it cooled. That, in itself, raised a question. Was the carbon dioxide that Webb had detected in August really a sample of the bulk composition of the body? Or was it the outermost layer, a frozen mantle of dry ice over a water-rich interior, the way some short-period comets in our system carry compositional gradients between their surfaces and their cores? The answer was still unknown when this story was being written. It is one of several open questions that the data from the months around perihelion will require years to fully resolve. There was finally one observation that had to be made retroactively. After the discovery of 3I Atlas in July 2025, several teams went back through the archives of survey telescopes to look for pre-covery detections, images of the object taken before anyone knew to look. The Zwicky Transient Facility at Palomar Observatory in California had imaged the comet on multiple nights in late May and June. The TESS satellite in Earth orbit on a different mission entirely had also recorded it at a heliocentric distance of about 6.4 astronomical units in May, 2 months before official discovery. Most strikingly, the Vera C. Rubin Observatory on Cerro Pachon in Chile had imaged 3I Atlas on the 21st of June, 2025, during the final commissioning phase of its LSST camera. Rubin had not yet begun science operations. It was still being tested. And it had photographed an interstellar visitor before any human knew the visitor was there. Now, let us hold that last point. The Vera C. Rubin Observatory is the most ambitious survey telescope ever built. Its name honors Vera Rubin, the astronomer at the Carnegie Institution, who, in the 1970s, measured the rotation curves of spiral galaxies and gave the world its first persistent evidence for dark matter. The observatory that bears her name was conceived in the late 1990s, funded through the National Science Foundation and the United States Department of Energy in the early 2000s, and constructed across the next 2 decades. Its primary mirror is 8.4 meters across, with a unique 3-mirror configuration that gives it both a wide field of view and a sharp focus. Its camera, the LSST cam, is the largest digital camera ever built. It contains 3.2 billion pixels, arranged across a focal plane the size of a small car. The observatory's primary mission, the Legacy Survey of Space and Time, will image the entire visible southern sky every 3 nights for 10 years. Every faint moving object brighter than about magnitude 24 will be catalogued. Asteroids, comets, transient phenomena, distant galaxies, and yes, interstellar visitors. The expectation, before Rubin came online, was that the survey would discover 1 or 2 interstellar objects each year. Some early estimates went higher, suggesting that visitors like 3I Atlas might pass through the inner solar system many times per decade, and that we had simply been blind to most of them. The Rubin pre-covery image of 3I Atlas, taken in June 2025 during commissioning, was the first hint that those estimates were right. The instrument that would soon be cataloguing the sky every 3 nights had already, accidentally, caught what it would soon be catching deliberately. What this means is something more than a statistical update. It is a change in the cadence of the question. Oumuamua in 2017 was a once-in-a-lifetime visitor. Borisov in 2019 was a second one, almost too soon. 3I Atlas 6 years later was the third. The 4th and 5th will arrive sooner. The 100th may arrive within a decade. The question that astronomers asked, when Wamuni Oumuamua passed through in 2017, was whether any human-built instrument would ever catch another one. The question that astronomers will be asking by the time Rubin completes its first full year of science operations will be different. It will be, which of these visitors do we follow with Webb, with the next great telescope, with which spacecraft, if any, can we ever hope to intercept? Atlas will never return. It is leaving on a hyperbolic orbit that will carry it slowly back into the interstellar medium. Sometime in the next several centuries, depending on which star happens to lie within range of its drifting trajectory, it may come within the gravitational influence of another solar system. More likely, it will simply continue on a path bent only by the diffuse gravity of the galaxy as a whole, falling through the dark between stars at 58 kilometers per second. It will never warm again. The carbon dioxide will refreeze. The water, what little of it the body still retains, will fuse back into its solid form. The comet will resume the long, cold journey it had been making for somewhere between 7 and 14 billion years before it dropped briefly through the warmth of a young sun. But it left behind a measurement, and the measurement is now in our records. That measurement is what changes the question. For most of human history, the answer to where the matter in our solar system came from has been the same answer: from the cloud that became our sun, from the disk that became our planets. The atoms in your hand are atoms that were synthesized inside other stars and redistributed by supernova explosions into the molecular cloud that condensed into us. The story has been told carefully by astronomers over the last century. The story is correct, but the story has always been told from the inside. The matter we measure is the matter that became us. Every measurement we have ever made of our own solar system is, in a real sense, a self-portrait. HRS is a piece of someone else's portrait. That is what makes the carbon dioxide measurement different from any other carbon dioxide measurement we have ever made. The carbon dioxide in 3I Atlas was synthesized somewhere else, by chemistry under conditions we cannot directly observe, around a star that may or may not still exist. Its ratio of carbon dioxide to water tells us something about that other place. Its dust composition tells us about the temperatures and pressures it formed under. Its kinematic age tells us, approximately, when the formation happened. And the timing answer places that formation within the first half of the universe. That is a number worth holding. There is a mission already being studied at the European Space Agency called Comet Interceptor. It is scheduled to launch in 2029. Its purpose is to park itself at the Sun-Earth Lagrange point, the gravitationally stable position 1.5 million kilometers behind Earth, and wait. To wait specifically for an interstellar visitor or a long-period comet to enter the inner solar system and then to fly toward it. The mission was conceived before 3I Atlas. It was conceived because the community had begun to expect that visitors would come more often than the historical record suggested. The early Rubin commissioning data confirmed that expectation in the most concrete way imaginable. By the time Comet Interceptor launches, the survey may have already identified the next interstellar object. By the time it has reached its waiting position, there may be 3 or 4 candidates in the queue. Atlas will, by then, be gone. Now let us go back to the beginning. On the night of the 1st of July 2025, at the Rio Hurtado observing station of the Atlas survey in the Chilean Andes, a half-meter telescope acquired 4 images of a patch of sky in the constellation Sagittarius. The patch was densely populated. It was looking toward the galactic center, where the stars are thickest and the signal to noise of any moving body has to fight against a wall of stationary light. The telescope was unattended, robotic. The images were beamed northward, across the equator, to the Institute for Astronomy in Honolulu. There, a software pipeline that John Tonry and Larry Deno had been refining for more than a decade compared the 4 frames against catalogues of known objects. The pipeline flagged a streak. It assigned the streak a provisional designation, 11PL3Z. The discovery, like all the consequential discoveries of the last 2 centuries of astronomy, happened first as a line of text on a screen. The wonder happened later. Larry Deno, in the morning of the 2nd of July, reviewed the queue. He looked at the streak. He noted its position, its motion, its brightness. He flagged it for follow-up. Within 24 hours, the Minor Planet Center had distributed an alert. Within 48 hours, telescopes on 5 continents were tracking it. Within 72 hours, the orbit solution had collapsed onto a number that was outside the realm of any object born from our sun. The number was the eccentricity, 6.14. Bound objects have eccentricities below 1. Long-period comets, returning after millions of years out among the Oort cloud, brush against eccentricity 1 but stay just below. To reach 6.14, an object cannot have begun its life in our solar system. The math is unambiguous. When Deno saw the orbit converge on that value, what he had found was the 3rd example, in the history of human astronomy, of a body from somewhere else. I think about Larry Deno sometimes. I think about him in the way I think about Robert Weryk, who in October of 2017, working through a similar early morning queue at the Pan-STARRS telescope on Haleakala, flagged the streak that became Oumuamua. I think about him in the way I think about Edwin Hubble at the Hooker telescope on Mount Wilson in 1923, finding the variable star that would eventually prove the universe contained other galaxies. I think about him in the way I think about Vera Rubin in the early 1970s, plotting rotation curves of a spiral galaxy and seeing the curves refuse to fall. These were not dramatic moments. Nobody shouted. Nobody knocked over a chair. The instruments did what instruments do. The data sat where it sat. And one person, in a quiet room, with no particular expectation of finding anything that day, noticed something they could not immediately explain. The story of astronomy, when you remove the press releases, is mostly this. Tired people in quiet rooms looking at numbers that took a long time to arrive. The numbers do not announce themselves. The numbers do not know that they are important. They are simply patient. And they wait for the right human at the right screen on the right morning. What still stops me about 3i Atlas is not the carbon dioxide. It is not the speed. It is not the age, although the age is, by any measure, the most staggering single fact about the object. What still stops me is the asymmetry of the encounter. We saw it. It did not see us. The comet passed through our neighbourhood and did nothing to mark its passage. It did not change course. It did not signal. It did not flare. It simply continued along the path it had been falling on for somewhere between 7 and 14 billion years, briefly warmed by an unfamiliar star, briefly photographed by instruments that the species which built them had not even existed for most of the time. The comet had been travelling, and then continued. The instruments observed. The comet did not observe back. There is a particular kind of loneliness in that geometry. We have built telescopes that can see across the universe. We have built spacecraft that can image objects from inside the orbit of Mars. We have constructed survey systems that can detect a kilometre-scale body in the dense star field of Sagittarius from the data accumulated in a single night. And the thing we caught with all of this looked, from its own perspective, at nothing. It simply fell through warmth and out again into the cold. This is the relationship between an observation and a universe that is not aware of being observed. The light arrives, the instruments record, the data are filed, the cosmos does not pause to acknowledge what we have learned about it. And yet, the measurement is now in our records. When 3i Atlas finishes its slow exit from our solar system, it will pass beyond the heliopause and resume its drift through the local interstellar medium at 58 kilometers per second. Its trajectory will not return it to any star whose light we have catalogued. It will continue, more or less in a straight line, for tens of thousands of years before any other gravitational influence becomes meaningful. It will not be observed again by any instrument that any civilization on this planet will ever build. But the photons it sent us between the 1st of July, 2025, and the slow fade into the southern dawn sometime in 2026 have already arrived. The detectors of Atlas, of Hubble, of Webb, of Rubin, of Subaru, of the IRAM 30-meter, of the Green Bank radio dish have already absorbed those photons. The electrical signal has already been amplified, digitized, written to disk, transmitted across networks, opened on screens, analyzed, published, archived. The light is gone in the sense that it is no longer light, but the information it carried is now part of the permanent record of what we, on this planet, in the early decades of the 21st century, knew to be true about the contents of the galaxy. Atlas, on its own trajectory, has no memory of having visited us. The visit was a one-sided event, but it left a measurement, and the measurement is preserved. What I think we should hold when we hold this story is the recognition that the instruments are still pointed. Tonight somewhere, a telescope is open. Tonight somewhere, a queue of survey images is being processed. Tonight somewhere, an astronomer is in a quiet room looking at numbers that took a long time to arrive. The next interstellar visitor is, by every reasonable estimate, already inbound. It was already inbound when 3i Atlas was still in transit. It is currently somewhere in the outer solar system, moving toward a perihelion none of us has yet calculated, because we cannot see it yet. We will see it. In its first full year of operations, The Rubin survey may report a new interstellar candidate every few months. By 2035, the question of how often we discover them will have entirely replaced the question of whether we discover them. And by the time someone is looking back at the year of 3i Atlas, the catalogue will have grown long enough that 3i will simply be where the modern era began. The first interstellar visitor, Oumuamua, was a once-in-history surprise. The second, Borisov, suggested the surprise was not unique. The third confirmed that it was not even rare. The fourth, when it comes, will be expected. And by then we will have built the instruments that can do what we could not yet do with 3i. We will have a probe at L2 waiting. We will have spectrographs designed for the kind of unfamiliar chemistry an interstellar comet might present. We will have perhaps the patience and the agreement among funding agencies to send a spacecraft outward to meet a visitor in flight. That will be a different kind of story. But this story is the one we have. The third visitor. The carbon dioxide-rich coma. The thick disk origin. The 7 to 14 billion year journey. The instrument in Chile that saw it. The instruments around the world and in space that followed. The radio dish in West Virginia that listened and heard nothing. The probe at the sun that watched its tail extend through the corona. The Mars orbiters that turned to look as it passed. These are the facts. They are now part of what we know. If this story stayed with you, A-Like helps other patient listeners find this archive. There is more waiting for you in the playlist. Other objects, other distances, other questions that have outlived their askers. The light is still travelling. The telescope is still open. The conversation continues. Thank you for staying with me through this story.